Hey everybody, welcome back to chemistry. And so we're continuing on looking at redox reactions. And so what I want to address now is how to solve a particular problem that you'll probably see either on your test or on your homework. And so the problem is you'll be given, say, 5 chemical reactions, and you're going to have to identify which one is a redox reaction. Or it could be that 4 of the reactions are redox reactions, and you have to figure out which one is not the redox reaction. So as an example here, we have this chemical reaction, sort of a standard one you might see on your homework on your test. And so let's take a look at it. And so you can see the reactants there are silver nitrate. Another reactant is cobalt, that is elemental cobalt in its free form. They react and they produce 2 products, and so one of the products is elemental silver there, and then we have the other product, which is cobalt nitrate. And so you sort of have to figure out maybe if that's a redox reaction or not. And so I think the easiest way to do that is to figure out that for any element in that reaction, as you go from reactants to products, does the oxidation number change? If you find one element that does that, then it's a redox reaction. You'll probably have more than one element that may do that if it's a redox reaction. On the other hand, if you check all elements and you find that for each element as you go from reactant to product, the oxidation number does not change, then it's not a redox reaction. So there is some strategy to figuring this out as quickly as possible. So let me talk about that. So I would say the first thing you can do is look at the chemical reaction and just realize that as you're checking oxidation numbers, if you find one element in that chemical reaction that changes its oxidation number, it is a redox reaction. And you can stop right there. If you find one element that changes its oxidation number as you go from reactant to product, you've identified the redox reaction. And if you want to, you can stop right there. So another thing I might suggest is when you look at a chemical reaction, if you see that there are free elements in that chemical reaction, I would check their oxidation numbers first. And the reason is a lot of times when you see free elements in a chemical reaction, they will be changing their oxidation number. And so if that's the case, then you have a redox reaction. Another thing you can do is look at metals. Metals tend to change their oxidation number, so that is what I would check next. And also another helpful hint is if you see a polyatomic ion in the chemical reaction, if the composition of the polyatomic ion does not change as you go from reactants to products, that probably means that the oxidation numbers of the elements that compose the polyatomic ion, their oxidation numbers are not changing as you go from reactants to products. Okay, so let's go back to this reaction and figure out if this is a redox reaction. So what I'm hoping you might do is when you see this reaction, you say, okay, well, looks like we have a free element there on the reactant side, that is cobalt. Let's check that first. Let's see what its oxidation number does. And if you check it, what you'll find is that free cobalt on the reactant side, because it's a free element, has an oxidation number of 0. Now, if you look at cobalt on the product side, cobalt you'll see is part of an ionic compound. And so you might remember if you have an ionic compound, it will separate into ions. And then in that ionic compound, the cobalt charge is going to be 2+. Therefore, the oxidation number of cobalt as a product will be +2. So you're going from 0 to +2 for cobalt as you go from reactants to products. So yes, this is a redox reaction. So what I just said I wrote there. Now, you will probably also notice that there is another free element in this reaction. It's on the product side this time. This is silver. You can check that. And if you do, what you'll notice is that on the product side, it is 0, but on the reactant side, when silver is part of that compound, silver nitrate, its oxidation number is +1. So it's changing as you go from reactants to products. And then if you look a little bit more carefully, what you would also see is that within the nitrate polyatomic ion, which you see on both the reactant and product sides of the equation, the oxidation numbers of the nitrogen and oxygen atoms are not changing. Okay, so what I want to do now is go over to the computer and get some practice here of figuring out whether these reactions that I have here are redox reactions or not. So let's look at the first reaction here. So we have vanadium oxide is reacting with calcium to produce vanadium and calcium oxide. So the first thing I probably want to do is I want to identify any free elements and see if those free elements are changing oxidation number. So you can see on the reactant side we have calcium as a free element here. What I mean by free element is that calcium is not bound to a counterion in a compound. So for example, calcium on the product side is bound to oxide, and so therefore here in this compound calcium is not a free element, but calcium by itself is a free element. And so we can assign an oxidation number to calcium over here to be 0. Now let's check out if calcium on the product side continues to have an oxidation number of 0. How will we figure that out? Well, first you notice that calcium oxide is an ionic compound. And so you ask yourself, well, what are the kind of ions that are in this ionic compound? And so one of the things you might remember is that oxygen will be in the form of the oxide ion, so it's 2 minus. Calcium in this ionic compound is 2 plus. And you might remember that the oxidation number of a monatomic ion is just the same as its number charge. And so calcium's oxidation number is +2 here on the product side. So what you can see is that calcium changes its oxidation number. You've identified one element in this reaction that does change its oxidation number. So this is a redox reaction. Now, if you wanted to, you could check the other elements and see if they change their oxidation numbers. Let me just point out what the answers are really quick. So vanadium here on the product side has an oxidation number of 0. On the reactant side, I'm hoping you can figure out that vanadium has an oxidation number of +5. So you can see as vanadium goes from reactants to products, it also is changing its oxidation number. Now, how about oxygen? Well, oxygen on the product side, you have an oxide ion, so its oxidation number is going to be -2. On the reactant side, you can also work it out, and I'm hoping you'll figure out that oxygen as oxide also has an oxidation number -2. So oxygen is not changing its oxidation number, but because we found one element that does, it is a redox reaction. Okay, so let's go to the next one. So the next one is that we have hydrobromic acid reacting with potassium hydroxide produces water and the potassium bromide salt. So that looks like a neutralization reaction. So is this a redox reaction? Okay, so do you see any free elements in this reaction? And I don't, so we can't really check those. Next question, do we see any metals in this reaction? In this particular reaction, I don't see any metals either. Do we see any polyatomic ions that you see on both sides of the equation? Well, we have a hydroxide on the reactant side. We do not have a hydroxide on the product side, so we really don't see any polyatomic ions either. So what do we do? So what you have to do is you have to look at these individual compounds and then figure out the oxidation number for each element on the compound. So that takes a little bit of time. So let's look at HBr, which is hydrobromic acid. Okay, so do you remember how to figure out the oxidation numbers for this compound? Well, first you ask yourself, is this a ionic or molecular compound? Both hydrogen and bromine are nonmetals. So this is a molecular compound. So if that's the case, if you have any hydrogens or oxygens, you can assign their oxidation numbers to be +1 and -2 respectively. So we have a hydrogen here, its oxidation number is +1. Now you might remember that if you have halogens like fluorine, chlorine, bromine, or iodine, they usually have an oxidation number of -1 unless there's oxygen in the compound. So there's no oxygen in this compound, and so bromine, its oxidation number will be -1. So that's done. Okay, let's go over to potassium hydroxide. Here we have an ionic compound. Potassium is a metal, hydroxide is a polyatomic ion made of nonmetals. So you might remember that when potassium hydroxide goes into solution, you make potassium ions and hydroxide ions. And so the oxidation number for potassium is going to be the same as its charge, so it's going to be +1. You can work out what the oxidation numbers of hydroxide are, and I think you'll find that the oxidation number for oxygen is -2, and the oxidation number for hydrogen is +1. And that kind of makes sense because, look, you have one oxygen hydroxide, it's -2. When added to the one hydrogen's oxidation number of +1, that should be equal to the charge of the ion, which is -1, and it is, so that makes sense. Okay, water is a molecular compound. Oxygen in this class always has an oxidation number of -2. Hydrogen always has an oxidation number of +1. And then potassium bromide, this is ionic salt, and so I'm hoping you'll figure out that potassium has an oxidation number of +1 and bromide has an oxidation number of -1. And so if you look carefully at that chemical reaction, what you'll see is that for each element, the oxidation number does not change as you go from reactants to products. For hydrogen, the oxidation number is always +1. For oxygen, the oxidation number is always -2. For bromine, it's always -1. And so, no, this is not a redox reaction. So in the next one, we have a combustion reaction. We know that because you can see this hydrocarbon here is reacting with oxygen, producing carbon dioxide and water. Now, you'll notice that this equation is already balanced. And the way we know that is we have coefficients here in front of these compound formulas. And so if you see those coefficients, you can pretty much ignore them when you're thinking about oxidation numbers. You can forget about them. You can just look at the oxidation numbers for the individual elements without considering the coefficients. Look for changes of that to figure out if it's a redox reaction. So we can just forget about the coefficients here in this equation. Okay, so is there a free element in this equation? Yes, on the reactant side, we have oxygen. You see that oxygen is not bound to any other element, so that is a free element. So let's focus on oxygen and see if its oxidation number changes from reactants to products. And so here, as a free element, oxygen has an oxidation number of 0. Now, you can see that oxygen is in two different compounds on the product side. Let's figure out their oxidation numbers there. So you might remember is that when you have oxygen in a molecular compound, then its oxidation number is always -2. So it's -2 here, and it's -2 here in water. So you can see that the oxidation number of oxygen is changing as you're going from reactants to products. And so yes, this is a redox reaction. We'll move on to the next one. And so the next equation, we have sulfur trioxide reacting with water to produce sulfuric acid. Is this a redox reaction? Do I see any free elements in this reaction I can check first? No, I do not. Do I see any metals that I can check next? No, I do not. Do I see any polyatomic ions that are found on both sides of the equations? No. I see sulfate here is on the product side. I don't see sulfate on the reactant side. So what you have to do is check the individual oxidation numbers. Okay, so here we go. So SO3 is made of nonmetals. It's a molecular compound. The oxidation number of oxygen in a molecular compound is always -2. Can you figure out what the oxidation number of sulfur is? Well, there are a total of, it looks like, 3 oxygens each with an oxidation number of -2. So the total oxidation number of oxygen would be -6. So what must be the oxidation number of one sulfur be to balance the total of -6 from the 3 oxygens? It must be +6, all right? Now, water is pretty easy. Oxygen has an oxidation number of -2. Hydrogen has an oxidation number of +1. Now we go over to the product side here. And so in this compound, it is a molecular compound. Oxidation number of oxygen is -2. Of hydrogen is +1. What is the oxidation number of sulfur in this compound? Anyway, I'm hoping that you can work it out that the oxidation number of this sulfur atom should be +6. Let's check that. So the question is this: when you add two oxidation numbers of hydrogen, which are +1 each, to a +6 from the sulfur, what do you get? You get a +8. How about oxygen? Well, we have 4 oxygens each with a -2, and so the total oxidation number contributed by oxygen is -8. So basically, all the oxidation numbers cancel out, and it's 0 for the compound. And as you can see, this is a neutral compound as written, so we would expect a compound oxidation number of 0. So this is not a redox reaction. Okay, the final one should be pretty easy. What makes this problem easy is that we have monatomic ions, and you might remember that the oxidation number for a monatomic ion is basically the same as its charge. So iron 2+ has an oxidation number of +2, iron 3+ has an oxidation number of +3, so oxidation number of iron is changing as you're going from reactants to products, and so this is a redox reaction. But for tin, its oxidation number is +4. On the product side here, its oxidation number is +2. It's also changing. So this is clearly a redox reaction. Okay, thank you for listening, and we'll see you next time.